Hey guys, I wanted to make this little video real quick. This isn't a topic that we have to cover, but I wanted to just show you one problem out of section 2 here that has 3 or more variables and give you some hints on what you could do with what we know at this point. And so this is 3 and more variable solutions. Remember that when we did 2 variables and 2 solutions, when our system of equations looked something like what you see up here at the top, that we had a whole bunch of choices, right? We could do it graphically. We could do it with the substitution method. We could do it with elimination method. And we'll learn a couple more before it's over with, but that's kind of what we've got in our pocket right now. And graphically, we saw that we're drawing 2 lines, solving each of these for y equals whatever, plotting the first line, plotting the second line, and there will be a point that those two cross at. That intersection of those 2 points is the solution right there. So x equals 5, y equals 1 is the point that we're looking for. Okay. We did have the weird cases where there's no solution if the two lines run parallel to each other. We also had the case where there are infinite solutions simply because they are the same line. The red and the blue line lie right on top of each other, and it kind of ate the end there, but that's okay. When we go to more than 2 variables, now we're in 3-dimensional space or 4-dimensional space or 20-dimensional space, something like that. We might have a problem that looks like what you see up here. This one does have 3 variables, x, y, and z. There are 3 equations. You'd have to have at least as many equations as variables. So here where I have 1, 2, 3 variables, x, y, and z, I've got 1, 2, 3 equations. That would be the minimum number that I could have and still solve this thing. And I just kind of wanted to point out some of the possibilities. Maybe instead of drawing lines, when we draw in 3-dimensional space with x, y, and z, we actually get a plane if it's a linear function here. So if I let those 3 planes cross, it is possible that there is a single point there in the middle. The black was better, wasn't it? Where all 3 of those planes cross, and we would get a solution right there that would have an x value, a y value, and a z value. Okay. And just like we had the problems down here where there was no solution, infinite solutions and everything, we have a whole bunch of possibilities here. This is kind of like, this case right here is kind of similar to this, where those 3 planes run parallel to each other. There are no points of intersection. So this would kind of be the no solution case where everything's running parallel to each other. But you can see in these other two, I don't get a solution that solves all 3. Like right here, this one point satisfies all 3 equations. And I don't have a single point over here. I do get a line right here that might satisfy, let's say, the x and the y, or those first 2 equations would be a better way to put it. Let me put 1 and 2. That'd actually make more sense. And then the third one's over here, so it's not part of that. I can't find a solution that satisfies all 3. Same thing here. I could have this might be equation 1, equation 2, and equation 3 would be this guy. Again, there's no single point that satisfies that. So all of these are no solutions at the bottom. This would be the infinite solution case right here, where all of those do cross, but not at a point. They make a line with an infinite number of points on there that would satisfy that. So it's a similar idea. We're stretching that out to 3 dimensions instead of 2, but you could keep going. If you had 4 equations with 4 variables or 20 equations with 20 variables, then you could see how this would get very complicated. That kind of takes the graphing possibility out of the picture, right? Um, it's hard to draw these things in 3-dimensional space and reliably say, well, that's 782 or something. You're not going to be able to see that on a graph, and maybe with some kind of computer programming, that would be fine. But at that point, you're not really doing it by graphing anyway. Um, So if graphing is out, we've still got substitution, and I'm going to show you this problem right here with substitution method. What about elimination method? Answer is maybe, maybe depending on the situation and stuff. And we're eventually going to see something where we're not doing it yet, so don't worry about it. But if we write these as a matrix, that's almost like an elimination method expanded for these bigger problems like that. You don't have to worry about that right now, but that will be another tool that we'll put in our toolbox before this is all over with. Let me show you this one problem here, and then I'll shut up about this. All right. Here is that problem. And we're going to do this with substitution, but it's going to be a little more convoluted because it's not just solve one and plug it into the other one. We kind of have to solve two of these equations and plug it into another one. And there's going to be multiple pathways through this, but they'll all give you the same answer if you do everything right. So what I'm going to do here, let's just label these 1, 2, and 3 so we can kind of reference which one we're looking at. And the first thing that I would like to do here is to solve number one for x. And I'm going to try to do this without running out of room. So you can see that here's x minus 2y plus 3z equals 9. If I added 2y and subtracted 3z from both sides, then I would get x equals 9 plus 2y minus 3z. So there's another version of equation one where I've got x on the left-hand side, shove everything else over to the right. And why don't we do that for number two as well? And we'll also solve that one for x. So number two, I'm going to, why don't we leave the x here? I'll take these two terms, 3y and negative z, over to the other side here. So I'm going to subtract 3y, add z to both sides, and then I'm going to have to change the sign of everything because I don't want this negative in front. I want a positive x right there. Um, you can work through the gory details of that, but what you're going to get is that I will do the negative x here equals negative 6. Remember that I am moving these two over like that and putting them over there. Negative 6 minus 3y plus z like that. Once I multiply through by negative 1 all the way, I'll get x equals 6 plus 3y minus z. So all we did there was change all the signs. Okay. Now here's kind of funny thing that we can do, but if I take this equation and this equation right here, and this is not the only way to do this problem, but it will work. You can see how I've got x equals this stuff and x also equals that other stuff. That means I could set those two x's equal to each other, and I would get 9 plus 2y minus 3z is equal to 6 plus 3y minus z, like that. Again, the top box here is x equals some stuff. This is x equals some stuff. Those two x's have to be equal, so all the stuff on the right-hand side have to be equal, and that's all I wrote there at the bottom. And once we clean that up a little bit, I actually went through and solved that for y. So, um, and I put these in the other order, but let's subtract 2y from both sides. I'll try to make some notes here to show what I'm doing. This would be negative 2y. That'll cancel that. I'd have to do it over here as well. Okay. And I'd also like to subtract 6 from both sides. Again, we're trying to get y by itself. And no, it's not the only way to do it, but this will work. And then I'm going to add z like that to both sides. Let's see where that gets us and what we can do with that. 9 minus 6 would be 3. These canceled. I got negative 3z plus z. That would be a minus 2z. And then over here, I've got 3y minus 2y. is 3y minus 2y would be y. Okay. And so that's some progress. Okay. We took these three equations and we've cooked it down to where we've knocked out one of the variables. There's no more x in that. Okay. Believe it or not, that's progress and that helps. So, um, what we can do now that I've got one of the variables solved in terms of one of the other variables is I can use that and substitute that back in somewhere. And why don't we go into number three? We haven't used number three yet. Remember, we took number one and we took number two. I got to get number three in there somewhere. So I'm going to take this right here and plug that into number two. All right. So let's write out number three. Oop, okay. So here I'd have a 2 times x, and I already know what x is. I could use either one of these up here, but I'll take that top one for no particular reason. That would be 9 plus 2y minus 3z. Minus 3z. Uh, where did that come from? Why did I write that? Okay, we took this guy, shoved him in right here. Okay, I think I wanted the 5y. We've already done that. Yeah, yeah, I wrote the wrong thing here. Okay, take that back. I have 2 times x, and I'm using all of that for x. I got minus 5y. So here's my minus 5. I know what y is. It's 3 minus 2z. So we're going to take that and put that in here. That would be 3 minus 2z. And then finally, I've got a plus 5z stringing along right there. It's equal to 17. Okay, so now I have two equations with two unknowns, and I'm getting closer. Okay, still not done. Before we do anything drastic, eventually we're going to take this thing and plug it in down here for y. All right, but before we do that, let's clean up a little bit, and I won't take that step just yet. Let's tidy up here. When I distribute here, 2 times 9 would be 18. 2 times 2y would be 4y. 2 times negative 3 is negative 6z. We're distributing on this second one here. Negative 5 times 3 is negative 15. And negative 5 times negative 2z would be positive 10z. I'm adding 5z and I'm getting 17. Okay. Got a bunch of z's I can put together here. How many variables do we have now? Only two, but I've got a thing where I can plug y in and knock it all the way down to one, which is the whole game here. You got to be a little bit clever about this. Not saying I was, but and there are other ways, maybe even a better way. I'm going to put those three z terms together. So that would be negative 6 plus 10 would be 4 plus 5 would be 9z. Let's put that down. I'm looking for y terms now. The only y term is this guy. And so I'd have a plus 4y. And then I've got 18 minus 15 on this side. So that's going to be a 3. And then finally, I've still got the equals 17 over there. And this might be a good place to shove that value, 3 minus 2y. Take this thing and replace y with it right there. We're doing all this substitution. Again, trying to reduce the number of variables down to one so that we can solve this with just straight up algebra. And looks like we're there, doesn't it? There's no variables in that equation except for z. So we can solve for z here. And then once we've got z, we can, kind of shove everything back and forth into the ones we've already made up and get the answers here. I got a 9z. I'm distributing the 4 to 3 would be 12. And the 4 to negative 2z would be negative 8z. And then I've got a plus 3. That's equal to 17. Haven't changed anything on the right-hand side of this at all, but you can see that 9z minus 8z would be z. 12 plus 3 would be 15. Over here is a 17. I subtract 15, and I get z equals 2. Okay? We've got one of the variables at this point, which is a really nice thing, because now that I know one of them, I can take this back over here and plug it in and see how that'll give me y. So right there, kind of following that, I'm gonna keep staying red here because I've already made a big mess and I don't really have room. Well, I can put it right here. We had y equals 3 minus 2z. So now that I know that z is 2, I got 3 minus 2 times 2. That would be a 4, and y is going to be negative 1. I've got a second solution here. Another one of my variables is hammered out right there. And here again, you could go into either the top, either one of these that we had. I've got x as this in terms of y and z, both of which I know, or I could go into the other one. It doesn't matter. Go into either one. We did the first one before. Let's do the second one now. Doesn't matter. X plus 3 times y, that's a negative 1, minus z, which is a 2. And that's going to give me a 6 minus 3 is 3 minus another 2 would be a 1 right there. Okay? The solution to this problem is x equals 1, y equals negative 1, z equals 2, and that is a point in three-dimensional space that I don't care to graph for you, but you could see how we could do that. And even if you had a whole bunch more variables and a whole bunch more equations, you could kind of work your way through that if you had to. We do have a better way coming up. That better way is called matrices. And you could do that with row operations. You could do it with Kramer's rule. You could also do something called the RREF that's on your calculator. And I'll show you that when we get there, but not today. All right. Thanks for stopping by and have a great day. Again, this three-dimensional stuff is not so much on the test until we get to the matrix part, so don't sweat it too much. Thanks.